Hi, I am José Valim, creator of Elixir, and today I would like to talk to you about a new project called NX that stands for Numerical Elixir, and our goals for this project and how we are going to use this project and a couple of related projects to enable Elixir for numerical computing. Okay, so let's get started. NX at the moment, right, is this idea of numerical elixir, but it's also a library that comes with a couple things that we'll explore in this talk. NX is about multidimensional typed arrays, aka tensors. Okay, it's about numerical definitions, it's about automatic differentiation, and it's about just-in-time and AOT stage compilation to the CPU and the GPU. And this is exactly what we are going to explore in this talk. Those are the topics for this talk. And in order to show how those things work, what we'll do is that we'll live code a neural network from scratch. Now is a good time to make one disclaimer, which is, if we're going to live code a neural network, sometimes I'm going to gloss over the neural network details. I'm going to say something like, hey, we're going to use this formula, and this is the name of the formula, and we know that this formula is good, but to fully understand the formula and why it's good, you have to refer to some documentation or some reference online after the talk, okay? Because the focus is not necessarily the neural network internals. The focus is on the NX library itself. Okay, so let's do it. We have a lot to do, so let's get started. So what will our neural network do? We are going to work with Deminis dataset, and Deminis dataset is kind of like the hello world of neural networks. So as part of this dataset, we can find the digits, handwritten digits in grayscale, exactly as you can see here right now. We can see a 5, we can see a 0, we can see a 4. And the goal of our neural network is to look at those digits, okay? And our neural network should be able to tell us, hey, this is a 5, this is a 0, this is a 4, and so on, okay? So let's get started. Let's start live coding a little bit so we can get in the flow and see kind of how NX works, okay? So here I am on a shell that is running inside the NX project, and I can create a new tensor, okay, calling NX tensor, right? And we can see that the tensors, they have a type. So in this case, we have signed integers of size 64, right? And we have exactly one dimension with 3 entries, but you know, I can make this multi-dimensional, right? So for example, now I have 2 dimensions. I can add more elements in here, okay? And then we can access a row if we want, and then another element inside that row. So those are tensors, okay? And there's a lot of stuff we can do with those tensors. We are just beginning, but you can see it already has a reasonable API with a lot of operations and things that we can do with it, okay? So that's an X. So let's take a look. Since we're going to be doing image classification with our neural network, classification of those digits, let's try to load this data. Let's try to load those digits, okay? And in this case, I have Deminis dataset is public. I have downloaded the dataset to my machine, and it is right here in this gzip file. So let's read this file, okay? So let's read this file, and I know it's gzipped, so I'm going to go ahead already and unzip it. And I'm going to put this in a binary, okay? So I just load the file from memory. And I know that this file, it has a certain format. So let's use Elixir pattern matching to extract it out. So the first 4 bytes, it's a version ID kind of thing. We don't care about it. But then we have the number of images. Then we have how many rows the image has, and then we have how many columns the image has. All those are 4 bytes. And then everything else from this binary is going to be the images, a blob with all the images, one right after the other, okay? So let's do this pattern matching here. So right now we're just using Elixir. There is nothing specific to NX right now. And we can see that the number of images is 60,000. And then we're going to see that each image, they are 28 per 28, okay? So, all right, so now we got the data where we want, and let's put it in a tensor. So to put it in a tensor from a blob from a binary, we can call the from binary, and we need to give it a type. In our case, our images, they are just bytes. It's a byte, it's an integer from 0 to 255, telling us, 0 is kind of black. We can consider it being black. At 255, it's a white of where the handwritten digit is, okay? So let's create a tensor, okay, from those images. And you can see here that it created a really large tensor because we have, it's the multiplication of 60,000 per 28 per 28 because we have everything as a huge blob. But we can reshape it. We can give it some shape, okay? So let's reshape the tensor to be exactly what we expect, right? Which is the number of images, the number of rows, the number of columns. And now you can see it's a three-dimensional tensor with all the images kind of like batched together, right? And then the images following right after. And for us to see those images, you can actually use a function called toHeatMap that is going to return a heat map of this tensor. And when we call it, we can see that it is finally printing those digits, right? So we can see a 5, we can see a 8, we can see a 9, okay? So we can see those digits being printed by using NX. All right, so this is we are starting to learn more about NX API, but in practice, we are not going to work with a tensor that is three-dimensional. Okay, why? Because in practice, actually, we would work with a three-dimensional tensor in this case, but because our neural network is going to be a very simple neural network, it doesn't really care about rows and columns. A convolutional neural network would, but not ours. Ours is going to be very simple at the beginning. So we're actually going to reshape the tensor, okay? I'm going to reshape the tensor to be just the number of images and then the number of rows multiplied by the number of columns. Okay? So when I do that, sorry, I have to pass the tensor as first argument. So when I do that, we can see, okay, we have all the images and then we have everything as if we had all of the bytes of that image in a row, okay? And the other thing that we want to do with this tensor in order to prepare it for our neural network is that because the numbers there are between 0 and 255, we don't want to feed that into our neural network, because if we start feeding large numbers, then they can start propagating, and then when we see we're going to be working with like infinity, and that's not going to be good, okay? We want to avoid that. So usually what we do is that we normalize the data, and we usually make it to be floats, okay, between 0 and 1. So we're just going to divide by 255, okay, and now we have normalized everything to be floats between 0 and 1. And the other thing that we are going to do is that although we have a super big batch with all the images, we rarely give all the images at once to the neural network, okay? What we do is that we break this big batch into small batches, okay? And then we give this small batch, this mini batch, and say, hey, train this and let me know your results, and then we configure things a little bit, and then we give the other batch. So we can call toBatched list, and that's going to return a list of those mini batches. And we want to say that each of those mini batches, they are going to have 30 images. So overall, we're going to have 2,000 mini batches, okay? So we can see now that we have this list of mini batches, okay? So cool. So we've played a little bit with NX, and what I'm going to do is that I'm going to get this code that we wrote, and I'm going to put it in a file as well. So in case I do something wrong, we can kind of continue from where I was. So just to recap, I have the data set in disk already. So I gzipped it, and I got some relevant information for us. And then we created a heat map, okay, from the binary, and then we reshaped it and converted it to a heat map. And then we also created a batch of images, okay, which is actually where we're going to fit our neural network. So we do that by calling from binary again, and we reshaped it to be just 2 dimensions, the batch images, and a row with all the image bytes. And here in this code, what I also did is that I gave those dimensions names, okay? And giving the dimension names is going to be really helpful for us to later to read the code and understand where we are doing our operations on, okay? So yeah, and then we normalized and we converted to a batch. All right, this is a good enough introduction to NX, so let's go back to our slides, okay? So our neural network, okay? So our neural network is going to be divided in layers. And we know that the input layer has exactly 784 units, right? So you can think that each byte of the image is going to map to a unit in the input layer. You can think like as if it was a neuron, right, in our neural network that we are going to load there. So for each byte, it's going to map to 1 unit, okay? And the input layer, therefore, has 784, which is exactly 28 per 28. And what about the output layer? How many units our output layer is going to have? You can think that you could say, hey, it's going to have 1 unit that is going to tell us if the image is a 0, it's a 5, it's a 7, and so on, okay? That could be a valid way to doing things, but that's not actually how we do things at all. So it's not necessarily a valid way. So what we actually are going to do is that instead of having a single number out, okay, we are going to have our output layer is going to have exactly 10 units. And those 10 units, they're going to return us probabilities, right? So it's going to be like, hey, I have like 80%, I'm 80% sure that this image is a 5, or I am like, 60% sure that this image is a 4. It's going to return probabilities. So the sum of the output should be 1 because each of them is given probability of how certain they are that that image represents a particular digit. Okay, and yeah. So the cool thing about probabilities is because if your output layer is saying, hey, I think it's a 5, but I'm only like 40% sure. You can, depending on the problem you're solving, you can say, okay, I'm not going to make a guess, okay? This is not good enough. So we want to output probabilities, okay? So we know how our input layer looks like and we already played with it. And now we know how we want our output layer to look like. So let's play a little bit with the output too. Okay, so let's go back to the terminal here. And the thing is, we have our training images, the images that we're going to train the neural network. So we also have the training labels, what we expect them to be. Okay, so so let's do that. Let's load the label data set. Okay, so again, it's going to be in the temp directory. So I'm just going to load it here really quickly. Okay, so, and we're going to pattern match the same way, okay? So the first 4 bytes we don't care, and then we're going to get the number of labels, okay? And we are going to get everything else from this binary is going to be just the labels, one right after the other, okay? So we want to pattern match on what we got from the gzip file, and we expect the number of labels to be exactly 60,000. Right? And then everything else, they are going to be labeled. So you can see 5, 0, 4. So the first image is a 5. The second one is a 0. The third one is a 4, which is exactly the image that I showed on the first slides. Okay? So let's put that in a tensor. Okay? So we already know we're going to use an X from binary. We are going to give it the labels. And the shape here seems to be unsigned integers as well. And this is going to give us a tensor with all 60,000 labels, right? But we know that this is not the format that we want, okay? Instead of a 5, we actually want something that says, because we are certain that it is a 5, because those are the labels, somebody look at the images and say, hey, this is a 5, right? We actually want to say, hey, there is 0 chance that this is the digit 0. There is 0 chance that this is the digit 1, okay? So we kind of want to say that, right? So it's not 0, it's not 1, it's not 2, it's not 3, it's not 4, and I'm 100% sure. So the probability for the number 5, right? We want that to be 1. We are 100% sure that that thing is the number 5. Okay, so we need to convert. We need to convert the tensor that we have right now. We need to convert to this list of probabilities, okay, where we are sure that certain image is 1, okay, we are 100% sure that it is that image. So to do that, the first thing that we're going to do is that we're going to use reshape again, okay? We're going to reshape the tensor, and we know we have exactly 60,000 labels, and we are going to wrap each of those labels in a list, okay? So this is what we get. This is exactly what we had before, but you can see that the 5 now is wrapped in a list, the 0 is wrapped in a list, okay? And we're going to create another tensor here right now, which are exactly the numbers from 0 to 9, okay? So we have those two tensors. And what we're going to do is that we are going to check where those tensors are equal. And where those are equal is exactly where the value matches, and we want that to be 100%. So at the moment we do this, we can see now, right, that instead of a 5, right, we are getting something that tells us that where the image 5 is going to be 0, 1, 2, 3, 4, 5. That's exactly 100%. So this is exactly what we want. And then at the end, we also want to call, right, to batched list, because if our training images, right, they are being batched, we want our labels to be batched as well, right? So we can call the same thing, and we're going to get the batches with our labels and so on. Okay. So yeah, so this is our label setup. So what I'm going to do is that I'm going to get the code that we wrote right now, and I'm going to put in our file, in my beloved backup file. And yeah, so we can see we are reading the file, gzipping it, and then getting the labels, loading to a tensor, reshaping the tensor, doing that trick. And this trick is called one-hot encoding, when we convert the label 5 to that list of probabilities where the number that we are sure it is 100%, is 1, right? That's called one-hot encoding, right? So this is the one-hot encode operation. And we are giving names when we reshape, right? We're saying, hey, this is a batch. The first dimension is the batch dimension, and then the other one is going to be the output dimension. And we convert to a list of mini batches, right? We convert to this batched list. Cool. So we've made some progress. We played with NX a little bit more. We learned new operations like NX equal. So we are ready to go back to our slides, okay? And we are ready to talk more about our neural network. So now we know our neural network has the input layer with 784. We talked about the output layer, which is going to have 10 units, okay? And now we need to say how we're going to connect those layers, right? How we're going to connect those layers with each other. We could try to connect the input layer directly with the output layer, okay? But if we do that, our neural network is probably not going to be able to learn anything at all, okay? So what we usually do is that we have hidden layers. So what we are going to add is a hidden layer of 128 units. And José, why 128? It's because a lot of people play with this data set, and we know that 128 is good, okay? If you were tackling a problem with a neural network since the beginning, those values, right, some of those formulas, you would have to figure it out yourself. But in this case, we know it's good, okay? So we're going to use this hidden layer. And what we're going to do is that we're going to connect each unit in the input layer to every unit in the hidden layer, and every unit in the hidden layer to every unit in the output layer, okay? And we are going to have to figure out the formulas that are going to allow us to do this, right? To do this connection. Yeah, but you know, so far what we have been doing is that we have been writing code in the terminal, right? And now that we are going to start to get more, we are going to start to get deeper into the neural network, we probably need a little bit more of a structure and a little bit more of affordances, conveniences to help us write this code. So let's talk about, before we jump to the neural network for real, let's talk about numerical definitions, okay? And again, let's talk about numerical definitions. We are going to do a little bit more of live coding. So, all right, so we are back here in the terminal, and here's the problem that we are going to solve very quickly. Imagine that we have this tensor, okay, this tensor t with 1, 2, 3, and 4, and we want to calculate, you know, the percentage of those numbers, okay? In this case, it's super easy, right? I can get t, and I can divide t by the sum of each element in t, right? And then you can see, sure, because the sum is 10, 4 is 40%, 1 is 10%, and that's a fine way of doing this, okay? But in neural networks, often what we want to do is that we want to we want to like accentuate the high values, like 4. We want to actually give 4 a bigger participation in the result, okay? And 1, because it's the smallest one, we want to give it a smaller participation in the result. So how can we do this? So one of the ways to do this is to use softmax, which we're going to implement using a numerical definition. So numerical definitions, they exist inside modules. Let me clear the screen a little bit so we can move things to the top. Okay, so numerical definitions, they exist inside modules. And all I need to do is that I need to import the nx_def_n module. And now what I can do is that instead of defining a function Elixir, which is with def, we just put a n here, def_n, okay? So this is a numerical definition, and it is effectively a subset of Elixir tailored for numerical computations, okay? So I'm going to define the softmax formula. It's going to receive the tensor, and softmax is that we are going to compute the exponential of each element in the tensor and divide by the sum of the exponential of each element in the tensor, okay? So that's our softmax formula. So now if I go here and call softmax passing the tensor, you can see that the percentage that it assigned to 1 now is like 3%, and the one that it assigned to 4 is like 64.4 effectively, okay? So that's it. And you can see that there is something really cool about the numerical definition is that we use the division operator, which in Elixir, it only works for numbers, but inside the numerical definition, the division operator is augmented to work with tensors as well, right? So this is one small convenience that we get with numerical definitions. And as we start writing more and more formulas, this is going to be very, very handy, okay? All right, so we've learned a little bit about def_n and how it works. So let's go back to our neural network, okay? So we know we have 3 layers. We have like the input layer, we have the hidden layer, and then we have the output layer. And we said that, you know, we need to find a way to connect, and we are going to connect all those layers, right? Each unit in every layer is connected to all the units in the next layer. And we know that the input, it's going to be mapped from the images that we have, right? So based on the value of the image, we are going to map the input layers. So what we need to do is that we need to compute the hidden layers. We need to compute the values of the hidden layers. And then when we compute the values of the hidden layers, we can compute the values of the output layer with hopefully the probabilities that we want, okay? So how are we going to do that? In order to compute the hidden layer, what we're going to do is that we're going to assign, for each of those connections, we are going to assign a weight, okay? So how many weights are we going to have between the input layer and the hidden layer? It's going to be exactly 784 per 128. We can think of it as a matrix, okay? A matrix of 784 per 128, okay? So here's the following. What is the mathematical operation that is going to take our input layer, which is a vector of like 784, is going to apply it with a matrix of 784 per 128, and is going to give us an output, which is our hidden layer, with 128 units, okay, 128 entries. What is the mathematical operation? It's exactly the dot operator, right? It's in this case, it can be like the operation between matrices, or in this case, the operation between a vector and a matrix, okay? So that's the formula, okay? That's the formula of our dense layer, about how our layers connect. We are going to get we are going to compute the dot operation between the previous layer and the weights, and that's going to give us the value of our next layer. And usually what we do is that we don't only do that, is that we also add a bias after the dot. So we have a little bit more parameters to tune our neural network, okay? And that's going to give us the next layer. So going back to our neural network, okay? We are starting to understand how to connect those pieces together, right? So we know that we have the weights and we have the bias between the input layer and the hidden layer, and we have the weights and the bias between the hidden layer and the output layer. And we know that we can compute the hidden layer with the dot product of the input and the weights plus the bias, and the output layer is going to be the dot of the hidden layer with the weights plus another bias, okay? So this is actually the formula of our neural network. So let's start implement that. Let's write that down, okay? So now that we learned about def_n, we can spend a little bit more time on the editor. So I'm going to define a module here that I'm going to call MNIST, okay? And what we're going to do is that we're going to define a predict function, okay? And this predict function, what we want it to do is that it's going to receive the parameters of our neural network that we know it's W1, B1, W2, B2, and the input layer, right? So, and because our input layer is a batch, let's call it a batch to remind us, right, that it is a batch of images, okay? So, okay. So, and we know that in order to compute the output, okay, we are going to start with the input layer, with the batch, and then we are going to do the dot product with W1, and then we are going to add the bias, and then we are going to do the dot product with W2, and then we are going to add the bias, okay? This is it. This is the formula of our neural network, or at least our first take at it, okay? And cool. But here's the thing. In order for our neural network to work, we need to give some values for those parameters, okay? We need to know how we are going to configure those parameters. And right now, we don't know how, okay? We actually don't know how. So what we're going to do is that I'm going to copy and paste some code here to save some time. But what we're going to do is that we're going to generate random parameters at first. We are going to start with random parameters. So exactly, so you can see here the weights. We are going to generate a matrix of 784 per 128, exactly what we talked about, right? With numbers between 0 and 0.1. And we know that the names of those dimensions is exactly input. So we have the input dimension and we have the hidden layer dimension, okay? And then we're going to generate random biases, the weight between the hidden layer and the output layer, and then the biases for the output layer, and that's going to give us all of our parameters, okay? And then we can start predicting. Let's actually give it a try, okay, then. So if we start with our neural network, so I'm going to do here is that I'm going to import this file where we have been dumping all of this code. I'm going to import it, and let's see what happens if we call MNIST. So one of the things that we can do before I call MNIST is that we need to get some batch of images, okay? I don't want to feed all of the batches right now. So what I'm going to do is that I'll go for our mini batch, and I'm just going to get the first batch of our mini batches. Let's call it first batch of images, FBI, okay? So if we get FBI here, you can see it's the first 30 images. And, okay, and we know that, and we know from this first 30 images, the first 3 should be 5, 0, and 4. Okay, so let's now call MNIST. So let's go back to our original journey. So MNIST predict, and we are going to give it the initial parameters because we don't have anything else. That's the best that we can do. And instead of giving the whole first batch, let's give like the first 3 digits in the batch because those are the ones we actually know what they are. Okay. So when we call this, you can see that, it returns something, but it's definitely not what we expect, right? Because we were expecting those things to return probabilities, right? To return numbers where the sum of this row here, it's 1. And you can see that that's not going to be the case, right? All those numbers here, they should be between 0 and 1. So what is happening? What is happening is that we forgot to do something, okay? We forgot to add the activation functions between our layers. So when we are connecting the layers, we get the dense layer formula, but before plugging the previous layer, the result of the previous layer into the new one, we usually wrap those layers, the formula of those layers, in activation functions, okay? And what would an activation function do? So for example, one activation function is the logistic function, which you can see has this curve. And one of the reasons why we use the logistic function is exactly, to keep the values between the layers, again, neatly contained between 0 and 1. So we don't have huge values flowing for our neural network, okay? So, let's do that. Let's add these activation functions, okay? So let's go back here. And then again, so this is how we get the hidden layer. So right after, I'm going to add the logistic function, which is actually part of an X. And then for the output layer, I need to add another activation function. Which activation function we're going to add, right? Remember that we want this thing to be probabilities between 0 and 1. okay? And remember that we most likely want to accentuate the high values and attenuate the low ones. So, and we learned that softmax does exactly that, okay? So let's use softmax. Softmax is not part of NX. So I'm going to paste the softmax formula here with one important change, okay? Remember that we are working with a batch of images, okay? So instead of summing all the values, okay, across all the batches, we want to sum and calculate the softmax for each entry in the batch, okay? So we say, hey, we actually want to sum over only the output layer, right? And we want to keep the axis as is, okay? So we keep the batch nicely. And all right, now we have added the activation functions. Let's go back to the terminal. Let's load the code again, and let's see if we have better luck. So let's reload the file, and now I'm going to call predict again. And as you can see, now it is finally returning numbers between 0 and 1. But you can see it doesn't make much sense, right? We know that the first image is a 5, but for some reason, our neural network thinks it's a 9, right? And because our parameters, they are random. Every time we call this, we are going to get something different, okay? Because our parameters, they are completely random, okay? So we need to solve that problem now. We know exactly what we need to do next. So before we jump into that, this is the formula of our neural network, okay? Those are the initial parameters. And now we need to figure out how we can customize, how we can tune those initial parameters so our neural network actually work as we expect. So let's go back to the presentation. So what we need to do is that we need to train our neural network, okay? And if you think about our neural network, you can think of something that, you know, it receives some input, and then the neural network has some parameters, and it has a mathematical formula of how it works that we just implemented, and then it's going to give us a output, okay? So we need to figure out what are the good parameters for our neural network, okay? And we know that the output is computed exactly as a function of those parameters and of the input. In order for us to be able to train our neural network to fine-tune those parameters, the first thing we need to do is that we need to find a way to see if our neural network is doing a good job or a bad job. Right? We need to say, hey, you know, those results were good, those results were bad. Okay. Luckily, because we have the training images, we have the training labels. Somebody went through those images and said, hey, this is a 5, this is a 0, this is a 4 for all the 60,000 images in the data set. Okay. So if we have the output and we have the expected output, we can kind of measure the loss function. We can kind of measure something that says, hey, you know, this is how bad the performance is of the neural network. So we can define the loss function. And if the loss function is a property of the output and the expected output, and the output is a property of the parameters and the input, it means that the loss function, we can implement it by receiving the parameters, the input, and the expected output, okay? So let's do that. Let's implement the loss function, okay? And to implement the loss function, so this is another part where I'm going to gloss over the details. We are going to use the cross entropy formula for multi categories, okay? And you can see why this formula is important, exactly what it means. You can search for it online. What I'm going to do is that I'm just going to implement it as is. So let's get started. So we are back here in our editor, and we are going to define the loss function, okay? And we know that our loss function is going to receive the parameters, okay? We know that it's going to receive the images that are our input, our batch of images, right? And it's going to receive the batch of labels, which are our expected output. And in order for us to get our actual output, okay, we just need to call predict with the parameters and our batch of images, and that's going to return our predictions. And the cross entropy formula, to compute it, we're going to get the log of our predictions and multiply that by the expected output, okay? And again, remember, this is a list of probabilities, so we want to get the mean of this list of probabilities, and we want to get over the output dimension, okay? So we don't want to do that over the whole batch of images. We just want to do that individually for each output. And then for the whole batch, we are going to sum over that. Okay, we're going to sum over the whole batch. So we are computing the mean over each output and expected output, and then that's going to return a value that we sum across the whole batch and get a negative number. Again, we are taking this formula as a given. Somebody figured out this for us. Somebody told for us that this is good. So that's what we are going to use. And the point here is that we are using the Elixir conveniences. Okay, we are using the multiplication operator. We are using the negate operator. Okay, exactly because we are inside fn. And that's our loss formula. Okay, so we have implemented. So what is next, right? Now with the loss function, we can say, you know, if our network is performing good or bad. Okay, we can answer this question. But it still doesn't tell us like how we are going to tune our parameters, right? How we are going to figure out how we are going to change our parameters so our new network gives us good results. The cool thing is, if we have a loss function, okay, if we have a loss function, we have a curve, okay? So what we need to figure out is we want to reduce the loss function. We want the loss to be as little as possible. So what we want to do is that we want to reach the global minimum of the loss function, okay? So imagine that when we have our random parameters, that is going to put us at some point in this curve, and we want to, you know, reach towards the global minimum. How are we going to do that? Okay, imagine that you are at the top of a mountain, right? And you want to go down, you want to go to the bottom as quickly as possible. You don't want to jump, right? You want to get there alive. But so how are you going to solve this? So what you do is that if you're at the top of the mountain, you look around you and you find a steepest slope down, okay? And you give one step in that direction, right? You give one step and now you're at a new position. You do the same thing. You find the steepest slope down around you and you give one step in that direction, okay? We want to do the same thing here for the loss function, right? The parameters are going to put us somewhere in this loss function, and then we want to give one step in the steepest direction, okay? In the steepest slope, in the steepest way down. How do we do this? How do we find the steepest slope for a mathematical function? Is with the derivative, okay? So if you can compute the derivative of this loss function, okay, we can figure out, you know, what is the steepest slope, and then we can give a step in that direction. So how are we going to compute the derivative, right? Every time we solve a problem, there is a new problem appearing, okay? How are we going to compute the derivative now, okay? Well, we could get a calculus handbook, and, you know, we have the loss function. It's a mathematical formula, okay? The predict function is a mathematical formula, okay? So we can go over these things, right? And compute the derivative by hand, okay? Which is going to be error prone, and we're likely going to make mistakes. But luckily, DefN has our back, okay? So let's go back to live coding, okay? So imagine that we want to do here is that we want to train our neural network, right? So we want to update every time we want to update our parameters based on the loss function. So we want to give it a batch, and then based on how good or bad the results are, based where those results put us in the loss function curve, we want to update our parameters so the next time we can do better, okay? So we're going to have a loss function that receives exactly the same, we're going to have an update function that receives exactly the same parameters as this loss function. So, you know, it receives the parameters, the images, which is our training set, and our expected results. And what we want to do is that we want to compute the derivative, okay? So this is the steepest slope, okay? We want to compute the derivative of the loss function, okay, as a property of the parameters, okay? So we want to compute the derivative of the loss function as based on each parameter that we have, okay? So what this is going to return, so in order to do this, in order to compute the derivative of a function, of a formula, which is this loss function that calls predict, all we need to do is to call this transformation that we have in the fn called grad, okay? And we give it the parameters that we want to compute the derivative on, and we pass the formula. And the reason why this works is because in the fn, we actually build an expression graph of all the computations that we are doing, okay? It builds a graph with all the computations. So when we need a derivative, we just traverse this graph computing the derivative of each operation that we are doing, okay? So what this is going to return is going to return us the gradient. You can think it's returning us like the steepest slope, right? This is returning the direction to us. So let's assign those gradients here. And now we have the steepest slope. So how are we going to update our parameters so we can reduce the loss function? We are going to simply give a step down in the direction of the steepest slope. So here is our step, right? Here is the steepest slope. And we're just going to give one step down. So we're going to slightly tune our parameters based on the gradient of the loss function. Okay, so copy and paste here. We're going to do that for each of the parameters. Okay, I'm going with the explicit approach here where we are changing all the parameters by hand. Of course, we could try to be a little bit more, indirect, but I think we are keeping it clear. We're updating each parameter by hand, passing all the parameters, computing the gradient. So this is it. With the update formula, now we can give the parameters, okay? We can say, hey, compute the derivative of the loss function that's going to give us the steepest slope, and then we can update those parameters so we can reduce the loss function. And this is it, okay? Our neural network is actually ready. We can actually train it, okay? So let's give it a try. So the first thing that I'm going to do is that first we need to zip, okay, the images and the labels, all right? We need to zip them together because those are, we have those mini batches, and then we need to put the inputs and expected outputs together. And I'm also going to give it an index, okay? So we know exactly which batch we are on right now. And the other thing that we are going to do is that now we can compute the parameters. So when we are training a neural network, usually we do that in epochs, so we do that a couple times. So what I'm going to do here is that I'm going to have 5 epochs, okay? And for each of those epochs, we want to go through, for each epoch, we want to go through all the batches, all the mini batches that we have. So let's unpack this thing that we zipped here. Let's unpack it here. And for each epoch and for each batch, we want to reduce over the parameters. And our initial value for the parameters is going to be exactly the random initial parameters, okay? All right, so for each of those, I want to print, okay? I want to print which epoch we are on right now. I want to print which bat we are on right now, and we want to call mnist update to update our parameters according to this particular batch of images and labels. And this is it. This is our training loop, okay? We're just going through the data set and we're training our neural network. So let's give this a try, okay? So it's allegedly ready. So let's import the file. Let's import talk.exs. And something did not work. And it is saying parameters do not exist on line 59, okay? And we are missing an assignment here. Fantastic. All right, let's go back to, let's import the file again. And you can see it is training, right? It's saying, hey, epoch 1, batch 0, epoch 1, batch 1. And you can see that this is taking forever, right? Remember that we have 2,000 batches, right? So this is not good enough. This is not satisfactory. This is going to take a long time, okay? And why it is so slow? It is slow because everything that we have been doing so far is happening in pure Elixir, right? We are manipulating binaries in pure Elixir, which is an immutable language, which means you're copying a lot of the binaries. So I'll cancel this. This is not going to finish on time for sure, okay? However, I have more good news. DefN has more surprises for us, okay? Exactly because DefN actually stores the computation graph, right, with all the expressions. We can actually tell DefN to use a different compiler. And one of the compilers that we have implemented, it's a compiler with bindings to Google XLA, which stands for a library for accelerated linear algebra. So by adding this one line of code and telling, hey, DefN, I want you to use the XLA compiler, we can try training our neural network again and see how fast this is going to be. So let's import the file. And now you can see it is much, 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 much faster. Okay, so now we are training our neural network, and in this case, I don't have a GPU here, and so it's if I had a GPU, it could be even faster. Okay, but we can see that this is already like orders of magnitude faster. Okay, because we are using the XLA compiler. So now we have the parameters. We have the parameters of our neural network. Does it work? I have to get the first batch of images again, so let's do that. And now if I call mnist predict with the parameters that we trained, and we give the first batch of images, and we want actually only the first 3 images of that batch, you can see here that 0, 1, 2, 3, 4, 5. You can see for the number 5, it's saying, hey, I am 70% sure it is the number 5, right? Which is really cool. For the number 1, it's like 95% sure, okay? And then for the number 4, it is 84% sure, okay? So we train our neural network, and I know that I'm testing the neural network with the training data set in favor of time, okay? But we could see how it works, how we build a neural network and train it all within Elixir, okay? So that's what I wanted to show. So before we can go, I just want to kind of sum very quickly what we explored and learned today. So today we talk about NX, and we learned that NX is multidimensional typed arrays, okay, aka tensors, and NX also provides something called numerical definitions, right, which are a subset of Elixir for numerical computation. And then it provides some like affordances, it gives us a little bit of a structure, and it also gives us things like automatic differentiation, and gives us things like just in time and ahead of time stage compilation to the CPU and the GPU, okay? DefN has many features in terms of affordances, okay? So it gives us like mathematical operators, we can do slices, pipes, module attributes. So while DefN is a subset of Elixir, tailored for numerical computations, it's actually a nice subset, right? It's a large subset well integrated into the language because we can use macros with import and aliases. We can do conditionals. So if you see a conditional in DefN, that conditional, it looks exactly like Elixir conditional, but it's going to run on the GPU, for example, if you use the XLA compiler. So again, everything in DefN is in the numerical world, okay? It's going to happen in the compiler of your choice. And when I say compiler of your choice, it's because one of the features is actually pluggable compilers. We have been using EXLA, which are bindings for the Google Accelerated Linear Algebra, but there are a lot of tensor compilers nowadays, and if you want to explore with different technologies, with special accelerators, this is going to give you the possibility to do so, okay? And before we leave, I just want to talk a little bit about how DefN works. Right, so when we wrote the softmax code in the terminal, where we did like softmax and then define the softmax formula, you could think that the way it works is that DefN gets the Elixir EST and translate that to the GPU executable, but that's not actually how it works, okay? It actually goes through multiple stages. So the way it happens is that we start with the Elixir EST, and then we transform and compile that to the virtual machine bytecode, compile it to Beam, okay? And it's regular VM bytecode. There's nothing special on it. And when you execute it, what we actually do is that we define the DefN AST. And this DefN AST then is just in time compiled to the GPU. And this allows us to do something really, really cool, which is the following. When you call a DefN, you are giving it a tensor that has a certain type and a certain shape. So when we compile to the GPU, what we do is that we get the shape of the tensor, we get the type of the tensor, so we know if it's a three-dimensional tensor, we know if it's a tensor of integers or a tensor of floats, we know those properties, and then we are going to compile to the GPU something specialized to the tensor that you are giving in, that you're passing as argument. We're not going to look at the values, we are interested on the shape and the type, and we are going to emit super specialized code for that, okay? And that's why the performance can be so good. Okay, thanks to this just-in-time compilation. All right, some party notes. you can see that I'm very excited about this, but as we're going to make NX open source today, I just want everyone to be aware that this is like early alpha software. There will be bugs, there's a lot of work to do, right? And as a reminder that this is beta software, when you're going to try EX layout, the first thing that you have to do is like to compile TensorFlow, which if you're lucky, it's going to take less than an hour, okay? But it usually takes a lot of time. You can have some gotchas in there. So we are early on, okay? I also want to show appreciation to a bunch of projects and folks. So first, NumPy and Google Jax. So you can think NX of today kind of being the junction between NumPy and Google Jax. So I really thank you for the teams that have been working on those projects, NumPy especially for so long. And a lot of the ideas that we found in Google Jax, we found them extremely interesting. So a huge thank you to them. Of course, a huge thank you to the Google XLA team that is allowing us that made this technology available and allowing us to see these massive speed ups. And a huge thank you to Sean, who has been working with me and those ideas for the last 3 months. And it's no exaggeration to say that this would not be possible. This would not have been possible without Sean. Okay, so thank you, Sean. And I just want to say that there is a really long road ahead of us. So if you're talking about having Elixir for using Elixir more for numerical computing, there's a lot of things to do, right? We need like plotting libraries, notebooks. We need to talk about other ways of doing things like supervised learning. Okay. Looking at NX itself, there's a lot of work to do. We don't support like complex numbers, for example. Not yet. We are going to do it in the future. Then we can add more functions for linear algebra. Maybe we should start looking at fast Fourier transforms. Maybe we can support other kinds of matrices, such as sparse matrices and so on. When we look at FN, there is a lot of interesting and cool stuff we can do with it. We look at grad, we talk about grad and how grad can look at this computation graph and compute the derivative for us. But we could do automatic batching, for example. So you can write code that doesn't know about batching and we batch everything for you. We could automatically compute inverses or compute Jacobian and Hessian matrices. And when it comes to backend and compilers, we are integrating with Google XLA right now, but we have been very careful to make everything pluggable. So, if you want to play with other ideas, if you want to play with libtorch, Apache TVM, or LVM, whatever is coming down the road, or custom accelerator, custom hardware, it's possible with NX because the whole library was designed to be extensible and pluggable. So that's what I had to share for today. Thank you very much for your time and your attention.